Today we're going to talk about just different system configurations that the Solmax all-in-one inverter can be used for. This inverter is a very flexible inverter. It can be used for a lot of different sorts of systems, from off-grid to various grid-connected, all the way from full net metered to backup, time of use, ones without interconnection agreements where the grid's only backup power for the solar. A lot of different options, and because it's so flexible, it really means that you need to know how to program it correctly for the particular system that you're actually building. And the first part of that is figuring out what are we really trying to do. You can't program it correctly if you don't know what kind of system type you're really trying to operate. And we find this a lot with people who they don't really understand exactly what they want to do with the system, and therefore the settings aren't right. Once we understand what we want to do with the system, how it interacts with the grid and other things, then we have a lot better ability to get the right settings. We'll be working on a series of trainings here on how to do those exact settings, and we're actually doing some changes to our app to make it easier, where you can kind of pick the system type and it gives you just the settings you need to modify for that system type. There's over 140 settings to program for this inverter, but usually anywhere between 3 and 4 and maybe a dozen at most are the ones you actually have to modify for a particular system type. The vast majority of all those programming functions are just left at the default values, but knowing which of the ones out of those to change is the important part. So this is the first video in a series of trainings on that. Over the next week or two, we'll be coming out with a bunch of additional materials for this. First part is figuring out which system type we need, and to do this we have this kind of flow chart, yes or no questions, and you can go through and see what kind of system type am I needing depending on details of mostly the grid and what you're doing with it. Zooming in on the top portion, we start up top here, and first question is there grid power? If the answer is no, then we go to all the off-grid options, and it's mostly a question of, do we have just off-grid with solar, or do we also have a generator, and where are we connecting that generator into the system? There's two different options there. If we do have grid power, then we immediately kind of do the UPS type systems. If we're not doing any solar, but we do have grid, then all we're doing is backup power. Then we have the UPS setup. This one can be changed to setups that do have solar later on. If we do have solar power and grid, then the big question is there an interconnection agreement with the utility? If there is no interconnection agreement with the utility company, then we're not allowed to operate in parallel with the grid, and that immediately puts us over in system type 2. We'll go through a little more details of all these system types in a minute. If we do have an interconnection agreement with the utility, then we get into a whole series of questions. Does it allow selling to the grid? How much does it allow selling to the grid? Going down farther, do we have net metering, and are there time of use rates, and are we allowed to sell battery power to the grid or just solar power? And if we have net metering, we kind of go through a bunch of those same questions. And also there's the question is, do we want batteries or not? Most of the time our inverter is used with batteries, but it is also possible to use it just as straight grid direct inverter. And why might you do this? Well, maybe you want the option to add backup power in the future, and to make it as easy as possible, instead of using an alternative inverter system, you can use our inverter, set it for batteryless operation, and it does just like any other string inverter would, but it's really easy to add batteries and backup power later. So that's a possibility there. And I'll put a link on the website in the documents that gets you to this little kind of questionnaire that can direct you to the different system types. Also want to mention we do have the new website. It's Solmax, sol-max.com, and it has a lot better access to a lot of the resources and documents. So I'd encourage you to check that out, and I'll make sure that all of these various documents that we talk about in these trainings are up on the website. These are kind of our 6 main types of PV systems that we can do with this inverter. Like we mentioned before, type 1 off-grid systems, if there's just no utility grid at all. Type 2 is when we do have the utility grid, but we don't have an interconnection agreement. So we're really using the utility grid kind of more like we would use a generator in an off-grid system. We're not interacting with it very much, except to use it as a backup power source if the solar is insufficient. Type 3 is grid connection systems, but no net metering. So either we have export restrictions, or in many cases we just have poor export value. So if we're selling extra solar to the grid, we're not really getting much money for it. So we really focus on how to use that electricity, use our batteries to avoid selling electricity to the grid as much as possible, even if we can do that. Type 4 is net metered systems. This is where we can sell power at the same rate that we're purchasing it. This is becoming less and less common as the years go by. There are still a lot of places doing it, but fewer than there were. There can still be cases when we have net metering where we do want to use the batteries in addition to the solar net metering, because we might also have time of use rates in the evenings in addition to net metering, and we want to avoid buying grid power at high rates in the evening and then selling it at lower rates in the midday. Even though we have net metering, the prices for that export is still lower than buying it later time during the day. And then kind of type 5 and 6 are our special cases. Type 5 is we're doing net metering, no batteries. We want solar now, and we're planning on adding batteries later for either backup power or time of use control. And type 6 is the UPS, where we're doing batteries and backup power now, and we might add solar in the future. We can also add a generator to this for additional backup power. Another possible use of this is if we have a certain sort of time of use metering where maybe for whatever reason we can't put in solar, or we're going to put it in later, we can use the batteries along with charging from the grid to avoid high time of use charges during a certain period, where it's kind of a UPS but also doing some time of use control. Off-grid systems, that's really the simplest. We divide this into 1A, where we have no generator. A lot of people want to do no generator off-grid. I always recommend having at least a small generator, even if you don't intend on using it much, because there's always some situation where the weather is just not cooperating and you can't control your loads well enough to just not use a generator. Like all the in-laws come over for Thanksgiving dinner in a big snowstorm, and you can't just turn everything in the house off to keep the batteries from going dead. You got to keep the lights on and stuff, so having a generator is recommended. So I don't usually recommend a complete off-grid solar without any generator, but it really does depend on your particular situation and how you can control the loads during the low production times. When we're using a generator, we can either connect the generator into the generator input, that's the smart load 1 on the inverter, or we can connect it into the AC input, which is the AC grid input usually. There's benefits and drawbacks of each of these different setups, and when we go through the separate training on programming for these, we'll talk about what makes sense. Do you want to connect the generator in through the generator input or through the AC input? And depends somewhat on what else you've got going on, but also what size generator you have, and are you relying on running really heavy loads direct from the generator or not. So like I said, we'll have a separate training that kind of goes through the details of these off-grid systems and how to program them. Looking at the next type, this is the type 2 self-consumption. We've got the grid available, but we really don't want to use it unless we just run out of solar power. And because we don't have an interconnection agreement, we can't operate in parallel with it. So we're essentially treating the grid as a backup generator in this case, and we want to wire that grid into the AC smart load 1 input, not the AC in, where it operates in parallel with that source. That means we can never accidentally backfeed the grid. All we're doing is basically switching back and forth between the grid and solar. And we program it so we obviously use our own battery power and solar as much as we can, but if we have to, we'll switch back to using the grid. It often makes more sense if you've got the grid available to use it as the backup rather than a generator, because even if you're paying $50 a month just to have the grid there and not use it, that's still usually cheaper than having your own generator and keeping up maintenance and fuel and all those costs that are associated with having your own generator on site. So that's really kind of the background between a type 2 system. Is it's really kind of like an off-grid system, but we do have the grid as backup instead of a generator. Now getting to the various type 3 systems, remember these are ones where we're allowed to sell to the grid, or we're allowed to at least operate in parallel with the grid. We've got an interconnection agreement, but it's not very attractive, the amount of money we get for selling power to the grid. First case, type 3A, is where we're actually not allowed to even sell to the grid. We're allowed to connect to the grid, but not sell to it. This is the case in some systems in California to avoid being pushed out of grandfathered net metered agreements with like an older system. If you expand, you're not allowed to sell anything from the expansion. And a lot of systems in Hawaii, you can put solar on your house, but you can't sell to the grid because they've got too much solar during mid-peak, and they're worried that'll destabilize the grid. So we can connect to the grid, but we can't sell to the grid. So we're operating very much like we just described for a type 2 system. We're operating from our own batteries, trying to avoid drawing from the grid as much as possible. And if the batteries get full, using the smart loads in the inverter to turn on opportunity loads, like that's when we turn on the EV charging or turn on an electric water heater just to store hot water, rather than just curtailing that PV production that we're not allowed to sell once our batteries are full. Often when you are dealing with a grid where you're not allowed to export, you might want to also look at a Type 2 configuration instead of a Type 3A. And we'll look at some of the benefits and drawbacks of what's the difference there. So the benefit of a Type 2 is that it has zero power draw from the grid if there is enough solar. Because it's switching back and forth between the grid, it never has any power draw when it's powering the loads from solar. A Type 3A, all the Type 3 systems, because they're operating in parallel with the grid, in order to make sure that it doesn't inadvertently sell to the grid at any point when loads change and solar input changes, it always has to have this background draw from the grid, such that when the power draw kind of bounces up and down, it doesn't inadvertently go below zero draw from the grid and sell to the grid. So a Type 3A is always going to have this small power draw from the grid, usually 100 to 200 watts, to keep that inadvertent sell back. So a Type 2, it's zero power draw from the grid if you've got enough solar. Now, the flip side of that is that if you have a lot of really big loads, if you're operating in parallel with the grid is really providing the surge for those big loads, and the inverter doesn't have to do that. If you're doing a Type 2, when you're operating from solar, the inverter is completely responsible for running that load, and because the grid is coming in on the 60 amp smart load, you've only got 60 amps pass through coming in from the grid rather than 100 amps when you're coming into the AC in. So if you're doing a system where your loads are smaller and you can really operate in fully off-grid most of the time and only occasionally use the grid, Type 2 might make more sense. If your loads are really large and maybe your solar is really not large enough to run the loads some of the times, then it makes more sense to do a Type 3A. You really rely on the grid a little more. And if you are relying on the grid fairly regularly, that small power draw all the time really isn't going to make that big of a difference. If you've got enough solar and small enough loads that you would almost never use the grid during summer months at least, then that small power draw of a Type 3A can really add up, whereas you could have absolutely zero grid usage if you did a Type 2. There's also some differences in how the AC coupled PV is affected. Type 3A cannot do AC coupled PV. So if you want to do AC coupled PV, maybe taking an existing PV array that has microinverters on it already, then a Type 2 can handle that, but a Type 3A that's not allowed to export to the grid cannot do that. If you want a lot of smart load ports to control various things, you have fewer of them available on a Type 2 because you're using one of them up as your AC grid input. And if you've got an AC coupled PV array, there's another one used up. You've only got your smart load 3 left. If you do a Type 3A, you've got all 3 smart load ports available, so you get a little more diversity of load control. So some differences where you do have an interconnection agreement. If you've got a big enough system and small enough loads, it may still make sense to do a Type 2 rather than a Type 3A. Type 3B is very similar to a 3A, only we can export some to the utility, just not the full amount of our PV array or an inverter size. This might be the utility requirements. Sometimes if you've got a really large system, the utility may say you've only got a 15 kVA transformer. So if you put in a 25 kilowatt system, you can't export more than 15 kilowatts to us because we're worried about our transformer capacity. Sometimes it's an issue that you're backfeeding a 200 amp panel, you can't backfeed it with more than 32 amps. So you need to limit that backfeed to 7,600 watts. So a Type 3B system, we can export some, and we can set a limit on that export to maintain compliance with limited transformer sizes, limited feeder sizes, or limited amperage of our interconnection point. Type 3C, here we're allowed to sell back, but we get paid really poorly for selling back. So we want to reduce the amount that we sell back, but we'd still rather sell back than curtailing that power, because at least we're getting a little bit for it. And this is quite common with a lot of utilities where they say, yeah, you can have an interconnection agreement and sell back, but anything you sell back, you're getting 4 cents for, and then you're paying 12.5 cents in the nighttime for what we sell you. So what we want to do is use the batteries as much as possible to power our own loads, and when the batteries are full, then we sell back, and maybe use some smart loads to do some opportunity dump loads if we can use it instead of selling back. Turn on the EV charging once the batteries get full, rather than selling back and charging the EV later from higher priced power. We want to make sure for any of these systems that we're like using our batteries instead of the grid, that we consider the cost of operating the batteries. It's about 5 to 6 cents per kilowatt hour cost of putting power into the batteries and drawing it back out. That's kind of the total lifetime kilowatt hours in and out of a battery divided by the cost of the battery. So if we're putting power in that is essentially 4 cents a kilowatt power, because that's all we would get by selling it to the grid, and then we're pulling it out to avoid buying power at 12 cents from the grid, there we've got an 8 cent differential. For 5 cents cost of battery, we're still making 3 cents a kilowatt hour on every kilowatt hour we put in and out of the battery, rather than selling to the grid and then buying back. So it makes sense. If the differential between buying and selling was only 3 cents, say they bought at 10 cents and charged you 13 cents, then it doesn't quite make sense to be using your battery instead, because everything you put into your battery, you're adding 5 cents to, and it's more expensive than just accepting that inequality in selling and buying from the grid. So when you're thinking about all these different cases where we're using the battery to save money, we need to think the battery isn't free. It is adding some cost to that electricity going in and out. But if that cost is less than the alternative of not using the battery, then that's where it makes sense. Sometimes we'll have a rate where you don't get paid very well for exporting, but you also have time of use rates where in the evenings you get paid, or you get charged really high rates. This is actually a lot of California right now. The NEM 3.0 is essentially very low rates for export and kind of medium high rates during most of the day, and then super high rates in the evenings. So there we want to make sure that we use the batteries for powering our own loads during those super high evening rates, and kind of preferentially use it then, rather than just saying anytime I can use the batteries instead of buying, I'll do that. So it's just a little bit more programming to preferentially use those batteries during the highest utility cost periods. And like I said, California and a bunch of other places are really where we start seeing this kind of thing a lot. Final type 3 type is very similar to what we just described, but we can also sell the batteries to the grid, not just the solar. So if it's a high enough price differential during that peak evening time and we're allowed to sell the batteries, it might make sense not just to cover our own loads with the batteries, but to dump those batteries into the grid. Obviously, we got to cover our own loads first, and then any additional that we have capacity for, we can dump into the grid and essentially be making money with that. If we're dumping into the grid at, say, 39 cents a kilowatt hour, and we charged it up either from grid power earlier that day at 12 cents or from excess solar, rather than selling that to the grid at 4 cents, you can see how that could be really attractive to essentially use our extra solar, charge up the batteries, and then sell that to the grid during those peak times if we're allowed to do that. Some utilities do allow that. They say, yeah, during those peak times, if you've got excess either solar or battery or whatever, we need the power, so sell it to us and we'll pay you for it. In the Northeast, we've actually seen a lot of utilities starting to do things where they actually want to control your batteries during some of those peak times, and they'll say, we need 2 hours of, can you discharge at 5 kilowatt hour or 5 kilowatts for 2 hours during this time period? And they send a signal out, and all the battery systems do that, and it becomes what they call a virtual power plant. Usually in those cases, instead of paying you a high rate for that, what they do is you'll get like a monthly incentive to participate in that program, or maybe it's an upfront cash incentive when you install the system. But it's kind of the same concept from a programming standpoint of you're dumping the batteries into the grid during a certain time. Again, you need to look at the difference in the rates to make sure it's worth using your batteries, thinking about that you're costing 5 cents a kilowatt hour roughly every time you use those batteries to put it in and then pull it back out on wear and tear of the batteries. Net metering is what we used to have a lot of and we're having fewer of now, but there's still a fair amount of places with net metering. And kind of this first type 4A, is what we always used to call net metered PV with grid tie with battery backup. Keep the batteries full all the time in case you have a power outage, and you just cover your loads and then sell any extra solar during the day. We do want to cycle the batteries just a little bit, maybe down to 95% each day, just because there's some issues if you keep them at 100% all the time with the BMS calibration and such. But generally, you're keeping the batteries just about full all the time and just selling power. So that's a fairly simple setup. It's used to be kind of the default and only setup for a lot of older inverters from Outback and Schneider, that was kind of what you did. The battery stayed full and the extra solar got sold. Now it's still a doable setup, but it's not the default that it used to be. Some places are still doing net metering, but with time of use rates, they also have a peak time in the evening. And here's where we want to kind of do a combo and say, we're going to draw our own local loads from the battery during that peak rate time, and then we'll wait for solar to charge it up, or maybe we'll use grid power to recharge it if that's allowed. Some grids don't want you using grid power to charge the batteries, which is confusing to me because they think it's fine to charge an EV or your computer with grid power, but they don't want your solar system batteries charged with grid power. Anyway, the goal here is kind of to say, we're going to do traditional net metering, but we also want to use our batteries to avoid buying any during that peak rate time, which is usually in the evenings after the solar production has declined. when we're trying to do this plus backup power, sometimes we have to think, how much of the battery storage do I want to use for my time of use avoidance, and how much do I want to reserve for backup power? Because what if I have a power outage that evening right after I drained the batteries, avoiding the time of use rates? You maybe could get away with one battery for doing just some backup power or getting through your time of use rate. But if you want to have enough capacity left for some good backup power and do your time of use avoidance, you might need 2 batteries instead of 1 battery on the system. So you kind of have to pick what do I want to use my battery for? Is it more important for me to avoid these peak time of use rates, or to keep that full for backup power? Type 4C is very similar, only we are allowed to export battery energy. So again, this is where instead of just covering our own loads, we might dump the batteries to the grid down to a certain point just to make money if they allow that. Type 5 is, like we discussed, we're doing net metering now, and we don't want batteries now. Often a cost thing. We're going to get the solar installed, get our system set up, and then we'll add batteries and backup power later. Or maybe backup power isn't the prime concern. Maybe we'll add batteries for some time of use shifting later. Or if we think we've got net metering now, but we're really concerned this utility is really trying to get rid of net metering, and within a couple years we probably won't have net metering anymore, this can add a lot of potential future-proofing value to your net metered grid tied system, in that when the utility says, guess what, we're now paying you 4 cents for your export instead of full net metered rate of 12 cents, you can add batteries and start doing a type 3 system. So it gives you a lot of flexibility versus putting in most of the grid tie systems that people are putting in now, where it's a little more clunky to add batteries or time of use shifting later, and adds a little more equipment. This way, all you've got to do is add the battery. If you're doing backup power, you have to add a backup power panel, and it's a bit less wiring later when something changes in the future for which type system you want. Another thing you can do is do a zero export system without batteries. This really relies on your loads kind of coinciding with when you have solar input coming in. Because obviously when you have no batteries, anytime the solar input is higher than your local loads, you're going to be curtailing solar input. But you could, say, one of these situations in Hawaii where exporting is not allowed, you could do a grid tie only system and just cover that daytime load, and that's another setup you can do with this. Maybe add batteries later, but you can at least get started and meet their zero export requirement and at least cut out a lot of that daytime load. Battery only UPS systems. This is a big thing where a lot more utilities are doing scheduled outages and just increased unreliability of the grid in general. A lot more people looking at backup power. And there's a lot of advantages and disadvantages of using a battery type UPS versus, say, a generator on a transfer switch. That's a whole nother discussion on how long are the expected power outages, what kind of generator do you have, what kind of loads do you have, are the loads kind of like heavy long-term loads, lighter loads, or heavy short-term loads. A lot of things kind of dictate whether a backup generator or a battery-based backup system really meets that best. A battery-based backup system using our inverter and batteries is going to have faster transfer time. You're not going to see that drop out for a couple seconds before a generator comes online. And for especially shorter term outages or light loads for longer term, like maybe it's only the refrigerator and the internet, stuff that's really kind of inefficient to run a larger generator for, is really good for battery backup. Long-term heavier loads, like say running the air conditioning during a long outage, might be better done with a generator because it can be more efficient when running a big constant heavy load. But you do always have the option of adding a generator to the battery-based system. The way our inverter is set up, you're doing your UPS system, and it can just auto start that generator, run it for an hour, recharge the battery, then shut it back off. So you're using your generator, but you're also using it in a much more efficient manner instead of running it 24 hours a day to handle loads which are much lower than its rated output most of the time. Instead, run it fairly hard for an hour, recharge the batteries, and then go for another 10 hours on those, and run the generator for an hour. So a combination of the generator plus the battery can actually sometimes get you farther than just a generator alone would. And you always have the option of adding solar to this. So depending on when you typically have power outages, solar can be a really good addition because it doesn't require constant fuel inputs to operate. So a lot of the situations, say with hurricanes, where 2 or 3 days afterwards it's bright and sunny, and fuel deliveries are a major issue for weeks often. But if you've got sun, then that can make more sense than relying on the generator. So doing our system with the batteries and the inverter gives you a lot more flexibility in adding different power sources into that backup power, solar plus generator, rather than really relying on just one of them. And if you do get the solar if you get the solar later and get an interconnection agreement, you could turn this into a Type 3 or Type 4 configuration depending on the utility, or it could even be turned into a Type 2 situation where it's not just doing backup power, but you're also cutting your bill down some even when the grid is there. So a lot of flexibility there, where you can start with just battery and backup power, but then go a lot of different ways in the future. Talk a little bit about details of AC coupling here and which systems work best with those. So as we discussed before, the Type 3A systems, zero export, are not compatible with AC coupled PV arrays. And that's because our inverter can't regulate the output of that AC coupled PV array and its separate inverter when it's also connected to the grid. So you do a Type 2 system where our inverter is not running in parallel with the grid, and then it can actually independently adjust the frequency to control that AC coupled PV array and turn it on and off. The Type 3B system, where we have limited output, then we have to have the AC coupled PV array needs to be smaller than the export limit because it can't regulate down from that maximum if it's trying to produce more than the export limit. Just about all the other systems are compatible with AC coupled PV arrays, either fully off-grid ones or any of the ones where we essentially are allowed to sell unlimited amounts to the grid, either at full retail for net metered ones or limited price for the Type 3 systems. Any of them that we're allowed to sell to the grid can handle an AC coupled PV array up to 12 kilowatts per each of our inverters, and that's limited by the 50 amp input breaker. When we're doing AC coupled PV arrays with off-grid systems, I always recommend also including some DC coupled PV array, and that's because it's really difficult sometimes to get the batteries up to 100% with an AC coupled PV array, because you need to very smoothly throttle that array back to just the right amount to finish charging those batteries to 100%. And usually that doesn't work. It depends on details of the exact inverter you've got on the AC coupled PV array and how that interacts with our inverter and the frequency shifting. But in my experience, usually getting those batteries higher than 95% is kind of tricky. It depends on the particular loads you've got and how that relates. But often you're going to have to set your stop value for your AC coupled PV array at 95% when you're off grid in order to prevent some system instability. What that means is that if you don't also have some DC coupled PV array, you're not going to be able to do that last little 5% of charging and get it up to 100%. The other reason to have at least some DC coupled PV on an off-grid PV array or an off-grid PV system is that if you get into a low battery situation and the inverter shuts down the AC output, then your AC coupled PV array will never turn back on because the inverter is waiting for the battery state of charge to go up before it turns the AC output on. But that AC coupled PV array, its grid direct inverter, is looking for the grid before it turns on, the grid being the AC output of our inverter. And if that never turns on because the battery state of charge isn't going up, then the PV array can't turn on. If you have some DC coupled PV, even though the inverter has shut off the AC output because of low battery, it will still accept that DC coupled PV array, start recharging the battery, and once it gets up to the recovery state of charge, it'll turn back on, also turning your AC coupled PV array on at that point. So for that issue of not getting stuck in a low voltage disconnect situation, I always recommend having some DC coupled PV on an off-grid system, and a type 2 system essentially being an off-grid system. Now, the ones that interact with the grid, the type 3 and 4 systems, those will also dark start from the grid if you've had a low battery shutdown. So that's less a concern there to have some DC coupled PV, because you can kind of rely on the grid a little bit more to handle that balancing, always absorb the extra from the AC coupled PV array. But when you are off grid or just using the grid as a generator type backup, you really have to think more about how can I recover myself from a low battery situation and not need that grid coming in, and get back to where my AC coupled PV array works. And that's where having at least some DC coupled PV array is a good design. And that concludes this training. Like I said, we're going to be doing a bunch more focusing on these individual things, and also coming out with a bunch more documents kind of showing here's exactly the programming for once you figure out, say, I want a type 3E system, how do I program that? And it'll go through exactly which set points or which settings and which set points to set on there. We'll be coming out with some various PDFs, which will be on the website under the resources tab. And also, like I said, working on the app to have kind of a quick set button that you say, here's the 10 things that I generally need to set for these basic setup of one of these systems, instead of going through pages and pages of settings to pick one out of each page. Because like I said, even though we've got 130 some different settings, usually it's a handful of them at maximum that you actually need to set for each particular one. We'll also be doing some sample wiring diagrams that show these different configurations, what's connected to what. Because like I said, we've got essentially two AC inputs, either the one marked AC in on the big breaker, or Smart Load 1, the one marked generator input. And it's not strictly grid into one and generator into the other. It depends on what kind of system configuration you want. Sometimes we run the grid into the generator input, and sometimes we run a generator into the grid input. And it just depends on what you want the system to behave like. So we'll be doing some sample wiring diagrams showing, say for a type 2 system, here's what connects to what and what amperages and what wire sizes are typically used there. Basically simplify, once you've figured out what do I want to do with it, how do you put it together, rather than going from the standpoint of here's everything it can do, but what do I want? I'm overwhelmed. And that has been a problem with the all-in-one inverter, because it is so flexible that figuring out how to program it for your particular situation has just been a little more difficult. So over the next few weeks, we'll be rolling out a lot of that, and we'll be sending out more emails to the training list. Check out our new website, soul-max.com, and let us know what you think. We're still working on fully populating it, but it should be a lot more user-friendly and easier to access a lot of these resources and training documents on there. Thanks, everyone.